And please, if anybody has any questions, just interrupt me freely. So a schedule for today. First, I'll introduce some notation, which I'll use throughout the rest of the talk. And then, of course, everybody here, I think, knows vastly more about torsors than I do, but for the sake of completeness, I'll say maybe something about torsors, which leads naturally into the notion of an invariant for algebraic groups. Often invariants for algebraic groups are computed for particular classes of algebraic groups with values in some specific functor. And so in section 3, I'll introduce the class of groups and the specific functor I'm interested in. In section 4, I'll get to the good stuff, namely the results of the paper. And then in sections 5 and 6, they'll be devoted to sort of a bird's eye broad view of the proof, with section 6 being devoted to examining a map, which will be first introduced in section 4. So as promised, the notation, F will just be a field of arbitrary characteristic, so no assumptions whatsoever on the field. G will denote an algebraic group over F. I'll write gamma to denote the absolute Galois group of F. And G sep will be shorthand for the base change of G to the separable closure of F. I'll write G star to denote the character group of G, which is to say algebraic group homomorphisms from G to the multiplicative group GM. And if A is a group, then I'll write A brackets N to denote the N torsion component of A. And just as a convention, all groups and schemes which appear in today's talk are affine unless otherwise indicated. So something about torsors. First, a definition. Let X be a scheme over my field F. A G-torsor over X is the data of a faithfully flat morphism F from E to X, such that the following 3 conditions hold. First, I have an action of my group G on E, as well as a trivial action on X. Secondly, I require that my map F be G equivariant, one consequence of which is that G act on the fibers of my morphism. And the third condition concerns how nice that action looks. And it says that for any F algebra R and any fixed point Y in XR, then the fiber over Y is either empty or the group GR acts simply transitively on the fiber. So all of the fibers somehow look like a copy of GR as far as GR sets go. The notion of a G-torsor is imitating a notion which is found in topology, namely that of a principal bundle. In topology, one has some total space projecting onto a base space, and the total space is equipped with the action of some topological group, such that the fibers of this projection down to the base space all look like a copy of that topological group, together with some coherence or local trivialization condition. And one can sort of see if you look at the definition above, this is just porting over that exact concept to the language of the functor of points. A morphism of G-torsors over X is just a G equivariant map of the total spaces, which respects the projection down to the X schemes, or projections down to X rather. And it's a basic result in the theory of torsors that any morphism of G-torsors is an isomorphism. So some more notation. I'll write tors X comma G to denote the set of isomorphism classes of G-torsors over X. And in fact, this is a pointed set whose base point is represented by the so-called trivial torsor, which is to say the torsor whose total space is G cross X and whose map down to X is just a projection onto the second component. If G is a commutative group scheme, then in fact we can upgrade the structure on tors XG to that of an abelian group. But just for the sake of simplicity, today I won't actually talk about what the group operation is. So it'll always be in the background, but I won't address it directly. There are sort of 2 components in tors blank blank, which one could change, which result in some sort of functoriality operations. First, I could change the base scheme. So for instance, if I have a morphism alpha y to x of F schemes, then I have a pullback morphism, which I'll denote tors upper star alpha from G-torsors over X to G-torsors over Y. And it just takes a representative E going to X to its pullback along the map alpha from Y to X. Likewise, I could also change the group in which case, if I have a morphism phi from G to H of group schemes over F, then I get a so-called change of group morphism towards lower star phi from G-torsors over X to H-torsors over X. And once again, this isn't too difficult to describe explicitly, but I'll just avoid doing so during today's talk. So one of the reasons why one might care about torsors, other than the fact that it's an analog of an extremely successful concept in topology, one sort of feature of the richness of the theory of torsors is that many equivalent formulations of the notion of a torsor appear throughout different contexts in algebra. And by looking at the passage of information between those different contexts, one obtains tools and ideas from seemingly different areas of math to bring to bear on specific problems where it wouldn't be otherwise apparent that they could be applied. So I've identified three settings here. The definition of torsors that I presented above is, I think, sort of fundamentally geometric in a certain way. But if I, for the sake of concreteness, look at, say, G-torsors over F, then this can be identified with sort of a cohomological interpretation, which is given by the first cohomology of F with values in G on the FPPF site. And in fact, if G is smooth, then one can actually replace this with Ital or Galois cohomology, but FPPF works for any G. And likewise, we have something coming from the algebraic side as well, which is if A is an F algebra, and we take G specifically to be the group of algebraic automorphisms of A, then this cohomology set is in bijection with the so-called twisted forms of A, which is to say isomorphism classes of F algebras such that when we pass to the separable closure, they become isomorphic to A. So some examples of this correspondence. If we take A to be the ring of n by n matrices over F, then Milnor tells us that the group of algebraic automorphisms of A is just PGLn. And classical Brouwer theory tells us that the twisted forms of A are precisely the F-isomorphism classes of centrosimple algebras over F of rank n. And on the geometric side of things, we have the sort of twisted forms of n-dimensional projective space, which correspond to Serre-Brouwer varieties of dimension n. And these are linked together by other common interpretation in terms of this first cohomology of F with values in PGLn. Another nice example is if you take A to be F to the n, well, then the group of automorphisms is just given by the constant group scheme associated to the symmetric group on n letters. Or the action comes from the permutation on this sort of standard idempotence. And in this case, the twisted forms of A are just those algebras such that when we pass to the separable closure, they become isomorphic to F sep to the n, which are exactly Ital F algebras of rank n. And again, on the geometric side, this sort of looks like just Ital n-fold covers of Spec F. And these are once again unified by their common cohomological interpretation. So if one accepts the notion that torsors are an interesting and beautiful thing to study, which I hope everyone does, then one is led naturally to the notion of an invariant. In topology, when one wants to study principal G bundles, an indispensable tool is the notion of a characteristic class, which is some sort of functorial association from principal bundles to certain singular cohomology classes, which give you geometric information about those bundles. And likewise, we can imitate that situation in algebra from the following functorial point of view. So say we restrict our attention to torsors over the base field F. And so I'll define a functor towards blank G from fields over F to set, which just sends a field extension L over F to the set of isomorphism classes of GL torsors over Spec L. And let H be any functor from fields over F to abelian groups. If we view H forgetfully as a functor to set, then the sort of Grothendieck'ian philosophy is that we can get information by the functor towards blank G by studying its morphisms to other functors. So one is led to the notion of an invariant. So definition, a type 1 H invariant of G is a natural transformation from towards blank G to H. And similarly, a type 0 H invariant of G is a natural transformation from G to H, where we view G as, we identify G with its functor of points restricted to fields over F. And just to explain the nomenclature of type 1 and type 0, it's really referring to what kind of functors tors blank G and G are, because in light of the interpretation of torsors as some sort of cohomologies above, you can view both of these functors somehow cohomologically, and the superscripts 1 and 0 refer to the type 1 and type 0 here. So just some more notation. The set of type I and H invariants of G form a group for I equal to 0 and 1, which I'll just denote by inv I, G, comma, H. In the event that G is commutative, as we saw above, we can view tors blank G as an abelian group valued functor. And so there's a natural subgroup of invariants that one can focus attention on. So precisely, if we say that an invariant I is homomorphic if it is a natural transformation of group valued functors. And this forms naturally a subgroup of the type I H invariants of G, which I'll denote by adding this subscript hom below the index. And so again, often the functor of interest H here is a functor arising out of cohomology in analogy with the situation in topology. I think when Serre initiated the study of cohomological invariants, these were the functors primarily of interest. So to give an example of how one might construct such an invariant in a particular case, thought I would present the example of a Stiefel-Whitney class. So suppose for this example only that the characteristic of our base field is not 2, and take G to be the orthogonal group. In this case, for any field extension L over F, the twisted forms interpretation of the isomorphism classes of G-L-torsors over Spec L is just that they are in bijection with isometry classes of non-degenerate rank n quadratic forms over L. So if I take H to be the functor Hn, I guess, motivic or FPPF with values in the group scheme U2, I'd like to produce an H invariant, a type 1 H invariant of G. So the first thing I'll do is I'll note that H1 of L with values in mu2 is sort of simple to describe, and I'll go through this in more detail later, but sort of standard Kummer theory tells us that this is isomorphic to the group of units of L modulo squares. And so I can construct a type 1 H invariant of G as follows. Any non-degenerate rank n quadratic form can be suitably diagonalized, and so it can be represented as a tuple of elements, non-zero elements of L. And this won't necessarily be a unique representation, but nevertheless, we can define the value of our invariant I on this representation by taking, for some tuple of coefficients alpha 1 through alpha n, units in L, we can take the cup product of their classes, corresponding classes in the units of L modulo squares. And even though the particular representation of our quadratic form in this diagonal form may not be unique in terms of the coefficients, it turns out that this assignment, in fact, is well-defined, and we correspondingly get an invariant. And this is just one example of one of the Stiefel-Whitney classes, but one can perform a similar procedure for different indices of cohomology for H by taking different symmetric functions in the cup product of the alpha i's. Okay, so moving on to the class of group schemes and functor I wanted to talk about specifically for today's talk. First, I need to introduce the notion of a diagonalizable group scheme. And so one says that a group scheme G is diagonalizable if the natural map from the group algebra over the characters of G to the representing algebra of G, induced by the inclusion of the characters of G into the units of the representing algebra, is an isomorphism of Hopf algebras over F. And so this definition is sort of quite formal, but the examples are quite nice. So to give two of them, the multiplicative group is an example of a diagonalizable group scheme, because if one looks at the representing algebra, then it's just the Laurent polynomial ring in one variable over F, which is isomorphic to the group algebra on Z via the map which sends 1 to T. And of course, the group of characters of GM is just C as well. And likewise, if G is taken to be mu-n, then in this case, the representing algebra is the polynomial ring in one variable over F mod the equation T to the n minus 1, which is again isomorphic to the group algebra over F of Z mod nz, which is exactly the group of characters of mu-n. And specifically, the map sends the class of 1 to the class of T. And somehow, up to taking products, these are all examples of diagonalizable group schemes once one chooses a suitable set of generators for the character group. So specifically, choosing a set of generators for finitely many generators for the character group yields an isomorphism with some product of copies of GM with some product of copies of mu-n for different n. The diagonalizable group schemes are precisely the twisted forms, or sorry, excuse me, the group schemes of multiplicative type are precisely the twisted forms of diagonalizable group schemes. So that is to say, G is said to be of multiplicative type if the base change of G to the separable closure is diagonalizable. And there's a very nice theory of groups of multiplicative type. Specifically, we have an equivalence of categories between algebraic groups of multiplicative type and finitely generated modules over the absolute Galois group. And the correspondence is the following. If we have an algebraic group G of multiplicative type, then we can consider its the character group of its base change to the separable closure. And this inherits a natural action of the absolute Galois group. And correspondingly, if I have a gamma module M, then I can consider the group algebra of M over F sep. And this has a natural semilinear action of the absolute Galois group. And so if we take the ring of gamma invariants, then we get an F algebra, and the spectrum of that F algebra represents an algebraic group of multiplicative type. And I should note that under this equivalence of categories, the subcategory of diagonalizable group schemes sitting inside groups of multiplicative type is equivalent to the subcategory of gamma modules with trivial actions. So that is to say the subcategory of finitely generated abelian groups. So that addresses us to the class of group schemes. Now to describe the functor, I first need to recall the definition of the ith Milnor K group of a field, which is just the ith tensor power of the units of F modulo the subgroup generated by tensors of the form A1 through AI, where for some index j, we have AJ plus AJ plus 1 is equal to 1. And the two most important Milnor K groups for the purposes of the talk today will be the 0th and the first Milnor K groups of F, which are given by Z, and the units of F, respectively. One can accordingly define two functors. The first is what I'll call Milnor K1 tensored with Q mod Z, which sends a field L over F to its group of units tensored with Q mod Z. And the second functor, which I'll call Milnor K1 mod N, which sends a field L to the units of L modulo nth powers. And just as a remark, these functors sort of do fit into the paradigm of the notion of cohomological invariants. And I don't want to sort of get into the weeds with defining the motivic complexes Q mod Z of 1 and Z mod N Z of 1, but I just should mention for the sake of completeness that there is a cohomological interpretation of these functors. And so there's a relationship between these functors as n varies. For instance, I have a natural transformation from Milnor K1 mod N to Milnor K1 tensored with Q mod Z for any positive integer n, which is just induced by the natural map from Z mod NZ to Q mod Z. And likewise, if n and m are positive integers such that n divides m, then I have a natural transformation from Milnor K1 mod n to Milnor K1 mod m, which is induced by the map from Z mod nz to Z mod mz. And under this sort of direct system of maps, we naturally have that the Milnor K1 tensored with Q mod Z is the colimit as n varies of the functors Milnor K1 mod n. So at last I have all the definitions to describe the words in the title. A degree 1 Milnor K invariant of G is then just an element of the type 1 homomorphic invariance of G with values in Milnor K1 tensored with Q mod Z. And likewise, a mod n degree 1 Milnor K invariant of G is an element of the type 1 homomorphic invariance of G with values in Milnor K1 mod n. And just so that I don't have to say the mouthful for the rest of this talk, I will call the first kind of invariant here a Q mod Z invariant of G, and the second kind of invariant just a mod n invariant of G. And hopefully there won't be too much confusion there. So the problem which I address in my paper and which I'd like to talk to you about today is to determine the group of degree 1 Milnor K invariants of G subject to the conditions that G be a group of multiplicative type. So on to the results. The first thing that I want to note is that we have maps from the mod n invariants of G to the Q mod Z invariants of G just by composing with these natural transformations from Milnor K1 mod n to Milnor K1 tensored with Q mod Z above. And because the natural transformations from Milnor K1 mod n to Milnor K1 tensored with Q mod Z are compatible as n varies, the corresponding map on mod n invariants to Q mod Z invariants are also compatible. And so we get a map out of the colimit as n varies of the mod n invariants to the Q mod Z invariants. And one of the first basic propositions in the paper is that, in fact, this map is an isomorphism. The utility of this observation is that it reduces us from the problem of trying to understand all Q mod Z invariants to understanding mod n invariants for some particular n and trying to find a suitable formula for them. And in fact, there's a nice recipe, which I'll now describe, for producing mod n invariants, which is quite formal. So there's a natural isomorphism, which I'll denote sigma n from mun-torsors over fields to Milnor K1 mod n, which comes from so-called Kummer theory. And I've written sigma n in one particular direction so that I don't have to write inverses everywhere later. But really, the map backwards from Milnor K1 mod n to torsor is sort of much easier to describe. And what it is it just takes for any field extension L over F and any class Y in the units of L modulo nth powers, it associates to that the torsor given by taking the spectrum of the polynomial ring in one variable, modulo the equation x to the n minus y, and projecting down to the spectrum of L. So with this Kummer theory isomorphism, we can cook up invariants via the following procedure. Suppose I'm given an n torsion character of G chi. This is just a map from G to mu n. And so I can associate to it a change of group map towards lower star of chi from G-torsors over fields to mu n torsors over fields. And if I compose that with this natural Kummer theory isomorphism, sigma n, then I obtain a type 1 invariant of G because these are just natural transformations from G-torsors to Milnor K1 mod n. So if I call this map phi G comma n, which sends chi to the composition of towards lower star chi with sigma n, the main result of the paper is that this map phi gn is an isomorphism for all n. So somehow this procedure describes all possible invariants and distinct characters produce distinct invariants. I should mention that this overlaps with independent work of Bertataro. He has a beautiful paper, Cohomological Invariants and Positive Characteristic, where I think he actually gave a talk on this paper in this seminar. And so he has many other wonderful results in that paper, but one result he has is theorem 15.2, which overlaps with my result. And he addresses the case where G is any affine group scheme, but there are some restrictions on the base field in N, namely that the characteristic of the base field is some positive prime P, and the integer N must be equal to P. So somehow it's more general in the sense that it addresses more group schemes, and maybe there are a few more restrictions on the base field and this integer n. Okay, and one can show that these maps phi gn are compatible as we vary the integer n. And so we obtain our computation of degree 1 Milnor K-invariance of G as follows. It's just isomorphic to the torsion characters of G. And this follows from our observation that the colimit as n varies of the mod n invariance is isomorphic to the group of Q mod Z invariants. So a fundamental ingredient in the theorems A and B is the following theorem, which might appear sort of unrelated at first glance. So first I'll state it. Let R be a smooth connected reductive group. Then we have an isomorphism, lambda n R, from normalized mun-torsors over R to type 0 mod invariants of R. And by normalized mun-torsors over R, I mean the subgroup of torsor classes such that the pullback along the identity point of RF is trivial. And so this probably looks a bit strange. It's not at all immediately clear why theorem C should be related to theorems A and B at all. And so for the rest of the talk, I'll try and answer two main questions, which is what is the relationship between this sort of strange third theorem and our main two theorems A and B? And another question is where should one use in the proof that G be of multiplicative type? Because in principle, this map phi Gn, which I introduced earlier, didn't use anything special about properties of G. So one could define this map for any group scheme, and it should be indicated where one needs that G be of multiplicative type in the proof. And so I'll try my best for the remaining two sections to address myself to these two questions. So beginning the outline of the proof, because G is a group of multiplicative type, so immediately using some properties of G, it admits an embedding into a quasi-split torus P, such that the quotient of P by G is also a torus, which I'll denote by T. And this is sort of just a basic result, which follows from this, this equivalence of categories between groups of multiplicative type and finitely generated gamma modules, together with the fact that this equivalence of categories preserves short exact sequences of, say, gamma modules and groups. So one has a corresponding exact sequence of group schemes, and this induces for every field extension L over F the following natural exact sequence. First, I have three terms just given by the points of each of the group schemes. And this can be continued one further to GL-torsors over L with the following boundary map. Suppose I have an L point of T X, which is just a morphism from spec L to T. The map from P to T is a G-torsor, and I can pull this torsor back along the point X. And this gives me a class in tors L, GL. And I can even continue this sequence one further by applying the change of group map from G to P. One might recognize this sort of six-term sequence as being analogous to the sort of long exact sequence one gets in FPPF cohomology from an exact sequence of group schemes. But we can be quite explicit here. The significance of this sort of exact sequence is that because PL is a quasi-split torus, by some Shapiro's lemma type argument, there are no non-trivial torsors over L. And so this last term, tors L PL, is trivial. So we have a four-term sort of exact sequence. And specifically, we get that the map from T to tors blank G is an epimorphism of functors. And so what this tells us in plainer language is that somehow the G-torsor from P to T is quite special in the sense that it encodes a lot more information than it might be apparent, in the sense that when one pulls the torsor, sorry, to start over, it has a lot of information in the sense that it contains all information about G-torsors over fields through pulling back points along these particular fields. And in fact, to be precise, we obtain the following exact sequence on invariance. which at each stage is just given by composition of functors. So we have a map from type 1 invariance of G to type 0 invariance of T, which is just given by composing with the epimorphism from T to tors blank G. And likewise, we have a map from type 0 invariance of T to type 0 invariance of P, just by composing with the map from P to T. And this sequence is exact by virtue of the fact that the above sequence of groups is exact, and the fact that this map is injective, this first map is injective, is just a consequence of the fact that the map from T to tors G is an epimorphism of functors. And so what this exact sequence allows us to do is to try to understand these mod n type 1 invariants of G in terms of their image sitting inside the mod n type 0 invariance of T. I have to be more specific to make this precise. So to that end, consider the following group homomorphism from the n torsion characters of G to normalize mu n torsors over T. And what it does is it takes an n torsion character chi, which is again a map from G to mu n, and it applies the change of group map associated to chi to the torsor G torsor P to T. I claim that the following big diagram is commutative and that both rows are exact. This lower row, we've already explained why it's exact, but I claim that the upper row is exact, and I'll get back to that in a minute. As the second map in the top row, we just have the pullback map on torsors from P to T. The two vertical maps are these yet to be introduced isomorphisms lambda n of T and lambda n of P. And the first map is our map of interest, this phi gn. So sorry for all the notation, but if one looks at this commutative diagram and accepts that it's commutative with exact rows, then one sees the import of theorem C in theorems A and B. Because if the vertical two maps, lambda n of T and lambda n of P, are isomorphisms, then a simple diagram chase will show that phi gn must also be an isomorphism. So there are a lot of things that I've sort of yet to explain here. The first thing is maybe why this top row is exact. And it's sort of, at least to me, on the face of it, mysterious why this should be so. But in fact, it's a bit technical, so I won't get into details, but you can reinterpret this exact sequence on the top row as arising out of some sort of Galois cohomology sequence. And so once one reinterprets this in terms of this sort of Galois cohomology sequence, the exactness becomes straightforward. And so the difficulty is showing that the two sequences, one arising from Galois cohomology and the one written here, are actually isomorphic. The other thing that I haven't really addressed is the construction of this map lambda n of T and lambda n of P, and given that, why this diagram should commute. And I'll say that once we have the definition of lambda n of T, it sort of is straightforward to see that the diagram commutes. So I won't talk about that. But for the remainder of the talk today, I will address what the map lambda n of R is for any reductive group and why it's an isomorphism. Okay, so at last, this mysterious map lambda n of R will be defined. Let R be just a smooth connected reductive group throughout this section. And so now I'll explain the connection between normalized torsors and type 0 mod n invariants. For any torsor class X in tors R mu n, I have the following construction of an invariant Ix. For any field extension L over F and any L point of R Y, I can pull back the class of the torsor X along Y, which gives me a mu n torsor over spec L. And then via the Kummer theory isomorphism sigma n, I get an element of the units of L modulo nth powers. And so this defines an invariant. And what is this importance of restricting our attention to normalized torsors? Well, one can see with some work that Ix is in fact homomorphic if and only if X is normalized. And so one of these directions is straightforward. If the invariant Ix is homomorphic, then its evaluation on the identity element of Rf, which I'll denote epsilon f, is just the trivial class. But by definition of Ix, its evaluation on epsilon f is just the pullback of x along epsilon f. And so in fact, this is exactly the condition that x be normalized. On the other hand, showing that if x is normalized, then Ix is homomorphic is maybe a bit more delicate, but I claim that it follows from the following formula, which is proved in the paper. And what it says is that for any field extension L over F and any points U and Y in RL, we have the following formula for the product of the pullbacks of X along U and Y. If I take the product of the pullbacks of X along U and Y, then it's the same thing as the pullback of X along the product of U and Y together multiplied with the pullback of X along epsilon L, which is again the identity element of RL. And so it's this sort of strange, almost multiplicativity relation, which is satisfied for all torsors. And for torsors which are normalized, this pullback of X along epsilon L is trivial. And so we get an honest multiplicativity relation, which shows us that Ix is homomorphic in the case that X is normalized. So now I can define lambda n of R. And all it does is it sends a class X in normalized mu n torsors over R to the invariant Ix. So now I'll explain the idea behind the proof of why this map is an isomorphism. So first, some notation. Let A denote the representing algebra of R. And let L be the field of rational functions on R, which is to say the field of fractions of A. And let C denote the generic point, which is just the canonical localization map from A to L. We have a map on invariants, which I'll denote by ev_c, which sends any invariant I to its evaluation at the generic point. And this map is quite useful and quite nice for a broad class of invariants. And so to make this precise, we have the following proposition. Suppose I have an invariant I such that for every field extension f prime over f and any 2 points x, y of R of f prime, we have the following almost multiplicativity relation for my invariant, which says that the evaluation of the invariant I at x multiplied by the invariant valued at y is the same thing as the valuation of the invariant at xy times the evaluation of the invariant at the identity point of Rf prime. Then, if the evaluation of I at the generic point is trivial, then our invariant I is itself trivial. So what this tells us immediately, in particular as an important consequence, is that the restriction of the evaluation map at the generic point to the subgroup of invariants which are homomorphic is injective. Because of course, any homomorphic invariant satisfies this almost multiplicativity property. In fact, it satisfies an honest multiplicativity property, which is quite a bit stronger. So this has a nice slogan, which is that these type 0 mod n invariants for smooth connected reductive groups are determined by their values at the generic point, which is sort of the sort of thing that one might hope for, right? In the sense that the generic point should control a lot of information about our group. And so trying to understand other points of the group in terms of these functorial associations should be possible in terms of the generic point. And so the point of studying this evaluation map is that now in order to understand these type 0 mod invariants of R, we can try to understand what their homomorphic image sitting inside the field of rational functions modulo nth powers looks like instead. And so to that end, let delta n of R denote the usual divisor map from the rational functions to the divisor group of R, mod n. There's a theorem of Mercuriev's, which says that the composition of the evaluation map on homomorphic invariants at the generic point composed with this divisor map is the trivial map, which is to say that this sequence that I've written down below is a complex. And sort of this says something about how for homomorphic invariants with values in, I guess, specifically Milnor K1 mod n, but any cycle module really should be unramified with respect to every discrete valuation. And so this theorem tells us something special about this image, namely that the image of the evaluation map at the generic point is contained in the kernel of this divisor map mod n. we need to get back to some relationship with the torsors. And so the key bridge is the following proposition, which appears in the paper, which is that the map, which I'll denote by rho r, from all mun-torsors over R to the field of rational functions modulo nth powers, which just takes a class to its pullback along the generic point and then applies the Kummer theory isomorphism, is in fact an isomorphism onto the kernel of this mod n divisor map. So what that is to say, mun-torsors over a reductive group R can be identified isomorphically with the subgroup of rational functions modulo nth powers, which have trivial discrete valuation at every point. And so because we just described that these type 0 mod n invariants should be accessible by understanding them in terms of their image inside this kernel, we need to build a relationship between torsors and the kernel in order to pick out which elements of invariance are actually hit by this map rho r. And I claim that it's just the image of the normalized mun-torsors over R sitting inside of mun-torsors over R. Specifically, we have a commutative diagram of complexes as follows, where the first map from mun-torsors over R normalized is just given by rho r. And then we have this complex that we've already seen on the bottom row. And the commutativity of this diagram already tells us something interesting, which is that the map lambda n of R is injective. The reason being that we just described that this map rho r is an isomorphism. So in particular, it's injective when restricted to normalized mun-torsors over R. And of course, the identity map on the field of rational functions modulo nth powers is injective. So just studying the commutativity of this diagram immediately tells us that lambda n of R is injective. Surjectivity is maybe a bit more complicated, but I claim that it actually follows from this proposition we introduced earlier about injectivity when evaluating invariance at the generic point for invariance satisfying this multiplicativity property. So suppose I have an invariant I, a mod n homomorphic invariant I, and I evaluate it at the generic point. Again, this lands somewhere in the kernel of this divisor map mod n. And so because rho r is an isomorphism, I can take the preimage under this map to get some mun-torsor over Rx, whose pullback at the generic point, suitably reinterpreted under this Kummer theory isomorphism, is exactly the value of I at the generic point. By the definition of the invariant Ix, if I evaluate Ix at the generic point, then this is exactly the pullback of X at the generic point. And by construction, we've chosen X so that this is equal to the value of I at the generic point. And so this proposition about injectivity when evaluating at the generic point for functors satisfying this multiplicativity criterion, this tells us now that Ix is in fact equal to I. And since the map lambda n sends any normalized mun-torsor X to Ix, we would be done if X were normalized in proving surjectivity. But I claim that this actually follows from the fact that I is a homomorphic invariant. And so just sort of looking at this formula, if we look at the pullback of X along the identity point of Rf, then this is just the same thing by definition as the value of the invariant Ix at epsilon f. But because Ix is equal to I, this is the same thing as the value of the invariant I at epsilon f. And because I is homomorphic, this must be the trivial class. So we obtain that X is normalized. And so in fact, lambda n of R of X is equal to I, which establishes surjectivity and completes the proof that lambda n of R is an isomorphism. And I think that's where I'll stop today's talk. So thanks so much.
Thank you very much, Alex. Are there any questions? Please feel free to unmute yourself if you have a question. Don't be shy.
I guess a naive small question. You were talking about this equivalence of categories, doing groups of multiplicative type and finally generated Galois modules. You had a module and you went back to the like gamma fixed points and you took a group algebra and the spec of it.
Right.
To get an algebraic group that should be a Hopf algebra, is the co-multiplication just the obvious elements of M get sent to like M tensor M and everything else is additive?
Yeah, so there's some, I guess, finicky business where you need to make sure that because you're taking gamma invariant elements, it's really going to be sums of these elements of M such that there's some invariance with respect to the gamma action. But yeah, that's exactly what you would think from sort of the naive multiplication structure that one defines for, say, diagonalizable group schemes.
Do you have any conjectures as to what degree 2 invariance might be?
We have something in the works. So there's sort of ongoing work with Professor Merkuriev, and the sort of, well, I guess maybe let me write something. So the degree 2 case is quite interesting, and we don't know, or I at least don't know, I should say, what it looks like for all groups of multiplicative type for instance, but at least the case of tori is quite interesting, and it looks like there might be some results here where if you have a torus T, and you look at the points of the dual torus over the base field F and consider the torsion points, then there's a way using some sort of cup product structure with torsors to produce an element of H2 with values in the motivic complex Z mod n Z1, or sorry, Z mod n Z2 rather. And so this gives you a map from these torsion points of the dual to type 2 invariants with, say, values in Milnor K2 mod n. And we suspect that the kernel of this map can be understood by taking a co-Flask resolution of the torus T and looking at the image under of the torsion points over the base field of the dual of some quasi-split torus in the resolution. But anyway, so the point is that up to some kernel, we suspect that the invariants look like these torsion points of the dual.
Any other questions? Okay, if there are no other questions, let's thank the speaker again.
Thanks so much, everyone, for coming.
And we'll reconvene again next week, the same time.